Hey guys, we are at the back half of Exam 2B. I'm about to do some lectures over Exam 2B information. This goes with the homework that says Assignment 2B or Exam 2B homework. I'm not sure how I phrased it. This is the second half. We did the big hard topics last time. We talked about definite integrals, what they mean, Riemann sums, how you estimate them. Today we're doing some applications of that idea. The plan is to have Exam 2B start this Friday. If that's too soon, let me know. I'm not strict on any of this stuff. It's a little bit soon for this lecture, but I don't feel stuck to 4 days seems soon. It would seem soon if we were meeting face to face, but we're not, so I don't know. If that's too soon, let me know. Hey, also, nobody's texting me anything. If you have questions on the homework, you can text me about them. If you have questions on this lecture, you can pause this video and send me a text. I'm not got a lot going on, so I'll probably get back to you pretty quickly. Right, let's talk about this. We got 3 big ideas to talk about today. The first of them is average value. So here's a motivating question. Start with this. If f of x is x squared, and if I pick a random number between 1 and 5, plug it into that f of x, so square that number, how big will that output be on average? Now, there's a couple words in here that are not clearly defined, but on average kind of leads you to do something silly and say, like, here's a wrong answer that feels right. Like, when I plug in, I know what x squared looks like. There's a part of it that I don't care about over here. But between 1 and 5, it's just, increasing. From f of 1 is 1 to f of 5 is 5 squared is 25. We're ending up with a random number between 1 and 25. So you would think the answer should be, what's the average of 1 and 25? It's 13. Is the answer 13? Probably not, because I said this is a wrong thing. Why is that not right? Well, think about what I mean by picking a random number between 1 and 5. The technical words are uniformly distributed. Which I'm not going to get into what all that means, but the short version is it means I should pick a number on the left half the time. I should pick a number from the right half the time. And further subdivisions. The left half of the left half should show up half of the time. When I pick these random numbers between 1 and 5, the frequency of getting a number between 1 and 2, that should happen 1/4 of the time because that's 1/4 of this interval. It doesn't need to happen exactly 1/4 of the time, but in the long run, like what we mean when we say that a coin has a 50% chance of coming up heads, is that if I toss it over and over forever, in the long run, the heads will come up about half the time, right? And closer to a half or something like that. So when I pick my random number, there's some built-in restrictions. And if I think about what the function is doing between 1, 3, and 5, 1, 3, 5, here I get 1, 3 squared is 9, 5 squared is 25. So if the answer was 13, that's sort of at odds with the fact that half the time I'm ending up with a number between 1 and 9, and half the time I'm ending up with a number between 9 and 27. Like, that contradicts the assumptions I was making when I said, well, it should be 13 because they're all equally likely. These 1 and 9 numbers, this is a gap of 8 that will come up half the time, or a width of 8. This is a gap of width, what is that, 16? That will come up half the time. So this spread of numbers is half the size of that spread, but it's going to come up just as often as that spread. So the numbers between 1 and 9 are coming up more frequently than the numbers between 9 and 25. So I think that points our answer should be lower than 13, because the smaller numbers are coming up more frequently than the bigger numbers between 1 and 25. If none of that makes sense, don't worry too much about that. But that's just sort of a little, how come it's not just the average of the top and the bottom? If I wanted to try to estimate this, what would I do? One thing I might do is pick numbers between 1 and 5. Like a thing I could do is I could pick 100 random numbers between 1 and 5 and plug them all in and average it. And that'll give me something pretty close to a good answer. But there's no reason to be stuck with random when Like if I'm trying to come up with an estimate, instead of doing them randomly, let's do them better than randomly and just sort of make them equally distributed. So let's say I cut the interval from 1 to 5 into 100 points. Evenly distributed. Between 1 and 5. What would I do with those points? I would call them like x0 or x1, x2, x3, all the way up to the last one will be x100. There's some details we could think about of how do I pick these points? Is it the middle of 100 intervals? Is it the left endpoint? It's the exact same questions we had last time. Don't worry too much about that right now. Just pick those 100 points equally spaced. What do I do with those points? I take those numbers, I would average them. So I need to plug them all into the function, add them up, and divide by how many of them are there? We said 100 points, so there should be 100 of them. That's how I would work it out in practice. I can split this fraction up. I have 1/100th of f of x1 plus 1/100th of f of x2. Up until the last one will be 1/100th of f of x100. And I see this is a thing that's almost a Riemann sum. If I was doing a Riemann sum for the integral of the function from 1 to 5, I would take a bunch of values, just like these, maybe left endpoints, midpoints, whatever you do, you get a bunch of values that should be about equally distributed, but we wouldn't multiply them by 1 over 100. What would we multiply them by? We would multiply them by, so this would be a Riemann sum, if instead of 1 over 100, it was, what should it be? Well, the gap from 1 to 5 is 4 units long. If we cut that into 100 equally spaced pieces, well, 4 over 100, well, 4 over 100. I don't need to simplify the fraction. If instead of 1 over 100, it would need to be 4 over 100. The width of each 100th of the I've got an interval of length 4, cut it into 100 equal pieces, you'll get little intervals of width 4 over 100 is 0.04. So I see I get the exact same thing as a Riemann sum, except off by a factor of 4. The average value should be about this thing, which I can multiply that by 1/4 and then multiply it by 4. So this 1/4 would cancel with those 4s, but the reason I'm uncanceling a thing that was simplified before is because this is a Riemann sum. So the average value is about 1/4 of the integral, and that's going to be our definition of the average value. Definition. So our definition is the average value of a function from somewhere to somewhere is given by 1 over b minus a, the integral from a to b of the function. And this does exactly the thing that we talked about. Pick 100 random numbers between a and b, plug them all into the function and average them, and you will get something close to this. The average should get more precise as you pick more numbers. If you pick them randomly, it'll work, but you can get there faster if instead of doing randomly, you kind of iron out the randomness by saying, pick them uniformly, This is the thing you get randomly, but you can do faster than randomly. The regular definition of an average of a bunch of numbers is you add up the numbers and divide by how many numbers there are. The thing we have is kind of like that. The fraction we have is on top is integral from a to b f of x dx. When we're integrating a function, we are kind of adding up all of those values. We're doing something like adding up all the values. There's infinitely many of them, and we're not getting an infinite answer. Uh-oh, time's up.